Hello everybody and welcome to our video on logarithmic functions. We just spent a lot of time talking about exponential functions, and we've also spent some time in the past talking about inverse functions. So all logarithmic functions is the inverses of exponentials. So since we know that exponential functions are one-to-one functions, we know that they must have an inverse. So we just use logarithms to notate those inverses. It just gives us a shorthand to describe the inverse of exponential functions. So, definition, if f of x equals a to the x, where a is positive and not equal to 1, then its inverse, called the logarithm base a of x, is written f inverse of x equals log base a of x. So hopefully we recall from our topics on inverses that there are two equivalent definitions for inverse functions. Both, of course, have the condition if f is 1-to-1. And in short, the first version of that definition was that when you compose inverse functions, you get back your input. And second was that inverse functions switch inputs and outputs. So of course, those definitions are just being restated here in this list. Y equals log base a of x if and only if x equals a to the y power. So you're just switching your inputs and outputs between the exponential form and the logarithmic form, and a to the log base a of x equals x, and log base a of a to the x equals x. So that's just the composition of inverse functions. So to be super clear about that, so if we've got f of x is a to the x, and f inverse of x is log base a of x, right? What this says is f of f inverse of x looks like a to the log base a of x. And we know by definition that f of f inverse of x is x. And it goes the other way around, of course. F inverse composed with f of x looks like log base a of a to the x power. Log base a of a to the x power is x, right? That's all it says. So let's go ahead and start tackling some problems using these definitions. So example number 1 here. Write 144 to the 1/2 power equals 12 in logarithmic form. So in other words, I want to get rid of exponents here and just write this as logarithms. And there's two ways we can do this. Either one is really just applying one of these two definitions. We can think of applying the first definition by switching inputs and outputs, or we can apply the second definition by taking log base 144 of both sides of the equation. And I prefer this approach as much as possible because it really reinforces this composition of inverse functions idea, which is the real important one. So log base a of a to the x is x. So log base 144 of 144 to the 1/2 is 1/2. 1/2 equals log base 144 of 12. So now we no longer have exponents, we have everything in logarithmic form, and we're done. Now, a couple quick things notation-wise. So when we talk about base 10 logarithms, that's the inverse of an exponential base 10, we just write log of x. So that means the same thing. It's just a shorthand, so we don't have to write the subscript base 10. And that's the common logarithm. Of course, our number system is base 10, so we use base 10 quite frequently in applications. Additionally, we also use base e a lot. We talked about that e, the value of e, and why e is the number it is, and how it relates to certain applications. So we also look at the inverse functions for e to the x, And so we write log base e of x short form as just ln of x, meaning the natural logarithm. Okay, so now we've got write 1 plus log of 10,000 equals 5 in exponential form. Well, in order to do this, first what I need to do is compact this form down. So I move the 1 across and I get log of 10,000 equals 4. I meant that parentheses to go here. So now remember, this is base 10. Even if we're not writing it, it's base 10. So if I want to write this in exponential form, I want to get rid of the logarithms. So I'm going to write 10 to the log base 10 of 10,000 equals 10 to the 4th power. So I just apply both sides of the equation into the exponent position, base 10. And then the definition says a to the log base a of x is x. 10 to the log base 10 of 10,000 is 10,000. So 10,000 equals 10 to the 4th. Again, everything we're going to do in this section, I want to really reinforce that. It's going to boil down to one of these two inverse function definitions. F of f inverse of x is x, or y equals f of x if and only if x equals f inverse of y. Composing inverses gives the input, and inverses switch inputs and outputs. Those are the two things that I really want to emphasize. Okay, so now let's take a look at this example 3. First, we'll start with evaluate log base 3 of 27. So what do I notice about 27? Well, 27 is actually a power of 3. So I can rewrite this as log base 3 of 3 cubed. And log base a of a to the x is x. X in this case is 3. So this is 3. So now let's take a look at b. We've got log base 3 of log base 2 of log base 5 of 25. So the first thing I'm going to do is rewrite 25. So this is log base 3 of log base 2 of log base 5. And 25 is the same thing as 5 squared. But log base 5 of 5 to the 2nd power is 2. Log base a of a to the x is x. So this is log base 3 of log base 2 of 2. Now, it's not written here, but if I have 2, that's the same thing as 2 to the 1st power. So when I look at log base 2 of 2 to the 1st power, that's 1, because log base a of a to the x is x, right? So this is log base 3 of 1. Now this one, there's two ways we could look at this. So we could think about the fact that 3 to the 0th power equals 1. So x is 0, y is 1, implies that log base 3 of 1 is 0. So here x is 1 and y is 0. Switch inputs and outputs. So log base 3 of 1 is 0. But we also could have considered the fact that log base 3 of 1 is the same thing as saying log base 3 of 3 to the 0 power, because 3 to the 0 power is 1, in which case we can go log base 3 of 3 to the 0 is 0. So either of those versions of the definition work here for evaluating this last expression. Okay, so let's go ahead and take a look at another example here. Now we're going to solve an equation. Solve log base 6 of x equals 2. So I'm going to solve this by first applying the base 6 and putting each side of this equation into the exponent position. 6 to the log base 6 of x is x. So x equals 6 squared, which is 36. Done. Next, solve log base 3 of 1 over 81 equals x. Well, in this case, it's already isolated equal to x, so solving it is just a matter of evaluating log base 3 of 1 over 81. So how can I do that? Well, 1 over 81. What do I know about 81? Well, I know that 81 is 3 to the 4th, right? And if you think something is a power, but you're not sure which power to, just literally do it and go 3 times 3 is 9, times 3 is 27, times 3 is 81. That's 4. 3 to the 4th power, right? And just count how many times you're multiplying by the number. Okay, now this is log base 3 of 1 over 3 to the 4th, but that's log base 3 of 3 to the negative 4th. So now we've got it in that log base a of a to the x form. Log base a of a to the x is x. So this is negative 4. Okay, so now let's go ahead and take a look at some more properties of exponential and logarithmic functions. This is just a summary. So exponential functions, we know that a to the 0 equals 1. Switch your inputs and outputs. That tells us log base a of 1 equals 0. Switch your x and your y. Switch your x and your y, right? We know for exponential functions that a to the 1 equals a, which means that log base a of a to the log base a of a equals 1. Again, switch your inputs and outputs. Input is 1, output is a. Input is a, output is 1. These are inverse functions, so if their inputs and outputs are switching, their domains and range are switching as well. So the domain for exponential functions was negative infinity to infinity, and range was 0 to infinity. So the domain for logarithms is 0 to infinity, and the range is negative infinity to infinity. Now, we knew that exponential functions had a y-intercept at y equal to 1, but remember, we're switching x and y values on these graphs, so that means that logarithmic functions have an x-intercept at x equals 1. And exponential functions didn't have an x-intercept, so logarithmic functions don't have a y-intercept. We knew that exponential functions had y equals 0 as a horizontal asymptote, but again, we're switching x and y values, so the logarithmic function has x equals 0 as a vertical asymptote. We knew that the exponential function was 1-to-1, meaning each input has only one corresponding output. So of course, if you flip your inputs and outputs around, it's still 1-to-1. The logarithmic function is also 1-to-1. We also get that both functions are increasing for a greater than 1 and decreasing for a between 0 and 1. Okay, so for example 6, we're going to take a look at the domain of some various logarithmic functions. The key thing to keep in mind is that typically log base a of x, the basic parent function, the domain is 0 to infinity. So we think of that as x being greater than or equal, x being strictly greater than, x being strictly greater than 0. So when we look at example A here, what do we know? It's the input that has to be greater than 0. That's the thing that's important, because here the input was just x. Now our input is x minus 5. So it's the input that has to be positive. So x minus 5 has to be positive. So x is greater than 5. So the domain is 5 to infinity. Now, when we look at part B, we have two logarithmic functions, which means both need to be defined for the sum to be defined. So we have to check the domain for each one of them. So let's take a look at x minus 1. We need x minus 1 to be positive, and we need 4 minus x to be positive. Well, what does that tell me? It tells me that x has to be greater than 1, and x has to be less than 4. So if I'm not sure where that happens, I can go ahead and just draw a little number line. Let's say here's 0, here's 1, here's 4, right? So x needs to be greater than 4. And x needs to be greater than 1. Or sorry, x needs to be less than 4. I can read my own writing. X is less than 4. It's going the other direction there. X needs to be less than 4. And x needs to be greater than 1. So the question is, where do these two overlap? And that's right in between here. So that tells me that the domain for this thing is between 1 and 4. Okay, so now we'll take a look at C, and we have a similar situation here, but our inputs are x minus 4 and 3 minus x. So we need x minus 4 to be positive, and we need 3 minus x to be positive. So x needs to be less than 3 here, and x needs to be greater than 4. That doesn't sound right, so let's go ahead and take a look here. So we'll mark 3 and 4 on our number line. And so we need x to be greater than 4. But we also need x to be less than 3. So the question is, where are both of these statements true? Nowhere, right? There is nowhere that these are both true. So the domain we say is empty. This symbol looks like a 0 with a line through it, means the empty set. So here we're saying there are no places where both of these functions are defined. So there's no x value that works for this function at all. Okay, now let's move on to part D. Find the domain of f of x equals ln of x minus 3 over x plus 2. So here, again, we need the whole input to be positive. Now this one's a little tricky because we have to think about fractions. When do we get a positive value for a fraction? So here we're going to kind of have to nest some things together, logically speaking. So as to say, a fraction is positive if both the numerator and denominator are positive. In other words, when I divide a positive number by a positive number, I get a positive. And also, when I divide a negative number by a negative number, I get a positive. So, we need either x minus 3 has to be positive and x plus 2 has to be positive, or so either both of these must be true, or they must both be negative. So keep in mind what we're saying here is here we're looking at these two both being true at the same time. So we need to look at the overlap where they are both true. And here we're looking at the overlap where they are both true. But then if either of the outer sets of facts are true, then the function's going to be defined because I'll have a positive input. So here x, if x is greater than 3 and x is greater than negative 2. Okay, well, when are both of these true? When x is greater than 3, right? If x is greater than 3, it's certainly greater than negative 2. Or, so either x can be greater than 3, or, well, here we get x is less than 3, and x is less than negative 2. So when are both of these things true? Well, if x is less than negative 2, it's certainly less than 3. So x is less than negative 2. So in other words, if either of these two conditions are met, this will be positive and the logarithm will be defined. So that means our domain is the combination of both of these intervals. So the domain should be the interval from -infinity to -2 unioned with the interval from 3 to infinity. Okay, let's go ahead and move on and take a look at the graphs of our basic logarithmic functions. So keep in mind, these first graphs look a little bit cluttered here, but that's because these first graphs that I've drawn have three pictures on them. They've got the line y equals x, they've got the original exponential function, and they also have the logarithm base a of x. So one of the things that we should keep in mind is that because inverse functions switch inputs and outputs, that means that they make a mirror image over the y equals x line. So we already knew what our exponential function looked like, y equals a to the x. So our logarithmic function is just the mirror image of that over that line. So when we had a horizontal asymptote at y equals 0, now we've got a vertical one at x equals 0. Now, on the other hand, when a is between 0 and 1, our exponential graph looked like this. And so when we flip that mirror image over the y equals x line, it looks like this green logarithm graph here. So let's go ahead and take out the extra information and just look at the logarithmic graphs by themselves. So these are our logarithmic graphs with our key points labeled. So again, this is log y equals log base a of x. So what do we know? We know that log base a of 1 over a equals log base a of a to the negative first power, which is -1. That's my first key point, which got moved somehow. Let me see if I can fix that. It does not want to let me. There we go. There we go. That's better. Okay, so when I plug in 1 over a as my input, my output is -1. That's just log properties, right? And when I plug in 1, well, we saw earlier, log base a of 1 is 0. That's that point. And log base a of a is 1. That's that point. So those are always going to be the three key points that you plot for your logarithms. They're just the inverse points for the exponential key points. So just like any other function, we're not going to plot a bunch of points. We're just going to plot the key points and use what we know about the function to shape the rest of the graph. Now notice, if we're looking at the a being between 0 and 1, all that does is change where a is on the x-axis, and that's why it ends up flipping this logarithmic graph over like this. So while we're here, let's take a look at these two facts, or 4 facts, I should say. For the graph where a is bigger than 1, the logarithmic function has 2 limit properties that when x approaches infinity of log base a of x, so when I go to the right, the y value keeps increasing, and so that limit is infinity. And when I approach 0 from the right, I trace down here, the y value goes down, so this approaches negative infinity. And on the other hand, when a is between 0 and 1, here the limit as x goes to infinity of log base a of x, that's going down, so the y value is approaching negative infinity. And when x approaches 0 from the right, the y value approaches positive infinity. So those are our basic limit properties and asymptotes for the logarithmic functions. Okay, so moving on, we're going to graph log base 2 of x minus 2 by transforming y equals log base 2 of x. So again, like always, we are going to start by taking the parent function, log base 2 of x, with no transformations. And we're going to graph this thing. So our key points, what are they? We know that log base 2 of 2 is 1. We know that log base 2 of 1 is 0. And log base 2 of 1 over 2 is -1. So we just plot those key points. And we also know that there should be a vertical asymptote on the y-axis. So this graph should look like this. And now our transformation is going to take this graph to y equals log base 2 of x minus 2. Take x minus 2 equal to 0 and solve it, and you get x equals 2. So this is a shift right 2. Oh, that's terrible. Let me try to draw that again. It's a little better. So as always, all I'm going to do is take my key points, move them over 1 each, or 2 each, I should say, move them over. So that'll go there, there, and there. And my asymptote is, since we're moving to the right and it's a vertical asymptote, it's going to move to the right as well by 2. And there's the graph of our function. Okay, so let's go ahead and move on to this next example. Graph y equals 2 minus 3 ln of x by transforming y equals ln of x. So again, as always, we're going to start by graphing the 3 key points. Question is, what are those key points? Well, remember the natural log is base e. So in this case, ln of e equals 1. Ln of 1 equals 0. And ln of 1 over e equals negative 1. So I'll plot e here in orange, and then this will be like 1 over e. Okay, so ln of e is 1. Ln of 1 is 0. Ln of 1 over e is negative 1. Got an asymptote on the y-axis, so the graph looks like that. And now we'll do our first transformation. So we've got ln of x. The next closest thing is the 3. So let's do that. Y equals 3 times the natural log of x. So remember, when you're multiplying the function by 3, all you're doing is multiplying all the old y values by 3. So you're essentially stretching the graph vertically. So here, where my y value used to be 1, my new y value is going to be 3. That's it. So this point's y value is 1, so it's going to go up to 3. Now, of course, the y value here is 0, so it's still going to be 0. 0 times 3 is 0. And here the y value is negative 1, so when I multiply it by 3, I get negative 3. Okay, so that was a vertical stretch by a factor of 3. And now we're going to look at y equals negative 3 ln of x. So now we're taking the previous y values and we're reflecting them, right, over the x-axis. So all that means is where this point was the negative point, I'm going to move that up to the positive. And of course, the negative of 0 is still 0. And then this point becomes negative. So now our graph is flipped over like that. Okay, and so now the last thing left to do is to look at y equals 2 minus 3 ln of x. And sometimes this can be a little confusing because you see 2 minus 3 ln of x, and it's not the way you often see these transformations written. Just keep in mind, this is the same thing as saying negative 3 ln of x plus 2, because we can add in any order. So we're adding 2 to the previous y value, so this thing is shifting up by 2. So then that's going to be it. We're just going to take this previous graph. And take each of our points and move them up by 2. Okay, that's it for that graph. So again, there's really not much new here when we're talking about graphing these logarithmic functions. There wasn't much new with graphing exponential functions. It's all the same transformation rules that we learned in general. It's only the starting graph that changes. It's the key points that you plot down at the beginning and the general shape that you start with. That's the only thing that's going to change, and all your other transformations will work exactly the same. Okay, so one more example here. We've got ln of 3 minus x by transforming y equals ln of x. So y equals ln of x. Okay, we graphed that one already, so I'm going to go real quick on this one. It's the same parent graph, right? This is e, this is 1 over e. So ln of 1 is 0, ln of 1 over e is negative 1, ln of e is 1. Graph looks like that. And now we're going to transform first to y equals ln of negative x. So now the negative is with our x, so we're reflecting over the y-axis. So just take all your values, flip them the opposite direction, all the x values, and move the points that way. Then we'll take this and we'll move it to y equals ln of 3 minus x. And remember, always take that input, set it equal to 0 and solve it, move that x across, and you get x equals 3. So this is a shift right by 3. So now keep in mind that since we've moved right by 3 and we had a vertical asymptote, that vertical asymptote has to move right by 3 as well. Now we take each of our points. So let's move our markers here over by 3. So that's our 1 over e minus 3. And then our e would end up here. So I shouldn't have marked all those extra ones. There we go. Okay, so we just trace those points backwards or to the right by 3. So that's going to go, this point will go 1, 2, 3. That'll go here. Let's do that in blue. And this one will be here. And this one will be here. All right, that's it for that example. Okay, so now we're going to talk about Newton's law of cooling. So Newton's law of cooling is one of many applications of exponential and logarithmic functions. And we did talk a bit about this, or we did an example related to this, I should say, in the exponential lecture video. So Newton's law of cooling states that the temperature at time t is equal to T sub s plus T naught minus Ts all times e to the negative kt, where T of t is the temperature of the object at time t, T sub s is the surrounding temperature, T sub naught is the initial temperature, the temperature at time 0, and K is a positive constant that depends on the object. So, in other words, this is just saying that, hey, whatever the temperature is at a given time is found by looking at the temperature around it plus the rest of this equation, which is the difference between the initial temperature and the temperature in the area times e to the negative kt. Now, this law, I believe, is derived using some differential equations techniques. So we can't actually do much with it here in this class in terms of deriving that, but at least we can see the law and we can apply this law. Now, we've rewritten this law below here in logarithmic form, which says that the natural log of t minus t sub s over t naught minus ts equals negative kt. Now, you don't necessarily need to memorize both of these. Like in particular, if you know one, then the other will follow very easily. So what do I mean by that? We'll look at T of t equal Ts plus T naught minus Ts e to the negative kt. So if I subtract Ts here, I get T of t minus Ts equals T naught minus Ts multiplied by e to the negative kt. So if I divide T naught minus Ts, I get T of t minus Ts over T naught minus Ts equals e to the negative kt. And so then if I just take the natural log of both sides of this equation, okay, what do I know? I know the natural log of e to a power is the power. That's negative kt. So this formula is just an algebraic rearrangement of this Newton's law of cooling for exponential functions. Now, which one of these is more helpful to you depends on the circumstance. In particular, if I was trying to solve for the time that had passed given temperature information about an object, then this logarithmic form is going to be more useful because it's going to be easier to solve for t. Or if I was trying to solve for the temperature constant that's involved here, this k, I was trying to solve for that, then again, this logarithmic form would be easier. So whichever one you use is just dependent on the context. They're both perfectly fine. All right, so with that, let's go ahead and take a look here at an example problem. A forensic investigator takes the temperature of a murder victim's body at 2:20 a.m. and found it to be 84.7 degrees Fahrenheit. At 2:50 a.m., the temperature was 83.9 degrees Fahrenheit. The air temperature that night was 54 degrees Fahrenheit, and normal body temperature is 98.6 degrees Fahrenheit. When did the murder occur? So this is a pretty standard thing that you see a lot in terms of criminal investigations, using this kind of technique to figure out things like this, time of death, for example. So let's first start out by listing what information we have, right? So that's important, is to figure out, hey, what do we know, all right? What do we know? Well, what I know is the initial temperature of the body would have been 98.6 degrees, right? The moment of death, that's the initial temperature. What else do I know? I know that the temperature of the surrounding area was 54 degrees. Now, I also know the temperature at two different times. The temperature at time 1. So the initial temperature, well, I shouldn't say the initial temperature, the temperature when the police arrived, when the investigator arrived, was 84.7 degrees. And then they took the temperature again a little bit later, and that was 83.9 degrees. Now, this is a little bit tricky because we have multiple different times here, but what do we know about those times? So the forensic investigator took the temperature originally at 2:20 a.m., and at 2:50 a.m. is when they took the temperature again. So that tells me that the second temperature is actually the first temperature plus 30 minutes. Okay, so now this is all the information I have so far. So what can we do with this? Well, remember, what are we trying to solve for? We're trying to solve for time. What was the, when did the murder occur? Well, if I can solve for T1, T1 is how long after the murder, right? So the murder we set as time equal to 0, T sub 0. So if I can figure out when T1 is, I know how long ago the murder occurred. So if I'm trying to solve for time, well, what did we notice earlier? That the logarithmic form of that law is going to be a little easier to solve for time. So what we're going to do is take this law, this is Newton's law, and we're going to apply the things that we know to the law and see if we can get somewhere with this. So first we're going to apply what we know about T1. So for T1, temperature at time 1, equal to 84.7 degrees. We're going to take that, and we're going to plug all the information we have into Newton's law here. So this gives us the natural log of the temperature at time 1, which is 84.7, minus the temperature of the surrounding area, that's 54 degrees, divided by the temperature of the body initially, it's 98.6 degrees, minus the temperature of the surrounding area, equals negative K times T1. Well, that gets me close. That at least lets me solve for T1 in terms of K, or vice versa. So, what can I do here? Well, I can divide out the T1, maybe. And if I know what negative K is, if I can figure out how to solve for negative K, then I'll be in good shape. So let's first figure out what this is. Negative, or 84.7 minus 54, that's going to be 30.7, divided by 98.6 minus 54, that's 44.6. And here I'm dividing by T1. So this is K. And we'll just pause there for now. So now we're going to look at applying Newton's law here to my other time, T2. But T2, again, that's actually T1 plus 30. And T1 plus 30, the temperature at T1 plus 30, is equal to 83.9 degrees. Okay, so now we just apply all the same stuff here. So what do we get? We get the natural log of the temperature at this time, that's 83.9 degrees, minus the temperature of the surrounding area, that's 54, over the initial temperature of the body, 98.6, minus 54, equals negative K times, now here we're taking the temperature at T1 plus 30, so we sub in T1 plus 30. Okay, so now let's do a little simplification. This becomes the natural log of 83.9 minus 54. That's 29.9 over 44.6. Okay, so now I've got this expression negative k times t1 plus 30 equals this, the natural log of 29.9 over 44.6. But I actually have a value for negative k, so we're going to substitute this in to this equation. This gives us the natural log of 29.9 over 44.6 equals the natural log of 30.7 over 44.6 divided by t1 times t1 plus 30. So now I just need to start simplifying this to solve for t1. It seems worse than it is. I'm going to start by dividing out this natural log expression. So I get ln of 29.9 over 44.6 divided by the natural log of 30.7 over 44.6 equals t1 plus 30 divided by t1. Okay, I can split this fraction up into t1 divided by t1. That's 1 plus 30 over t1. So I can subtract 1 and then divide by 30, and I get the natural log of this whole thing divided by this natural log minus 1 divided by 30 equals 1 over t1. Okay, now that looks pretty messy, but here I have two fractions, the right side, the left side, and I want to solve for t1, so I can just take the reciprocal of both sides of the equation. And that gives me t1 equals 30 divided by this whole thing. Okay, now the rest of this is like plug it into a calculator work. So I'll go ahead and do that real quick. And as long as I haven't made any silly mistakes in between here, we should be able to figure out our final answer. So 30 divided by, and if you've got a calculator that will let you put parentheses around all this stuff, it's definitely something you want to do. Go overboard with the parentheses so that you're not accidentally putting things in the wrong order. Okay, so I got approximately, so when I put that in a calculator, I get approximately 424.3 minutes. This is past our initial time, right? So if we want the actual time that things occurred, so T1 was really set at 2:20 a.m. So I want 424.3 minutes before that. So the initial time is 2:20 a.m. minus, well, how many hours is this? So if we take this and that's going to be 7+ hours. All right, so this is 7 hours and 4.3 minutes. So minus 7 hours is going to put us at, let's see, 12:20 minus another 5. That's 7:20 p.m. minus another 4. Okay, so sorry about that. Let me say that again. So minus 7 hours, that's going to put us at about 7:20 a.m. minus 4.3 minutes. That's, let's just say, about 7:16 p.m., I mean to say. Okay. Well, that's it. Thank you for watching.